Hello and welcome to another episode of the Func Prog podcast with me, Christopher, and today I have with me Matthias.
Yes, hello.
And that's how you pronounce your name, right?
Well, it's Matthias.
Matthias.
Matthias. In Iceland we have these silent H's everywhere that like we don't even acknowledge, but then when you try to teach other people, you're like, oh, why are you saying an H? And I'm like, I'm not saying an H.
Yeah.
But so it's very Matthias.
Yeah. Matthías Páll Gissurarson. Is that the...
Yeah, that's... So the second word is like, it's Pall. So there's like this sound. And it's... I discovered this recently. It's an Aztec sound. Or like, it's also in Aztec. So they say nahuatl.
Okay.
So... And I think also the original word for chocolate is like chocolate.
Ah.
So it's Pall.
Okay, yeah.
And it's like it's very hard to get people to say this. So I just say, Matthías Páll, and then, we roll with that.
Yeah. I'm sorry, my Icelandic is a bit rusty, so...
Yeah.
But yes, I mean, and today we're going to talk, about a bunch of different things, I guess. But it's probably going to be a bit of Haskell and program synthesis, and also, how that relates to AI and LLMs and things like that. But first of all, I'm gonna throw you a curveball. You're also the deadlift champion.
Yes. This June. In June I set the national deadlift record for my weight category. So I'm around 59 kilos, and it's like a special weight category for under 59 kilos. And then so I deadlifted 140 kilos, and then it's an official record. So, and it was also at the national championship. So I ended up becoming a national deadlift champion. And I think it's funny because it's just me and like one other guy in that weight category. And then that's the story. Like, he's my friend from school, like way back. Yeah, and I saw him posting on Facebook and be like, I just got a new record in deadlifting. And I'm like, wait a minute, I could beat that. And then, I mean, it took a few months, but I could beat that. So
Yeah.
And my favorite part is like, whatever happens now, I'll always be a former deadlift champion. You know? So.
But 140 kilos, that's crazy. That's a lot. I mean, that's almost like triple your... I mean, if you exaggerate a bit, like almost triple your body weight.
Yeah, I mean, so it's. I mean, I think it's about 2.4 as I calculated. And because another Icelander also set a deadlift record recently, the Mountain.
Yes.
But he's also he set the world deadlift record, right? He lifted like 505 kilos or something.
Yeah, that's a lot.
And then my first thought with that was like, because he's 200 kilos. And I'm like, that's not that far from my ratio, right? But, it's more impressive because nobody has done it before. But, I feel like, but then I watched we had like the IPF championships, the International Powerlifting Championships in Iceland. So they were hosting in Iceland last year, I think. And then they're like people who are my weight, and they're pulling like 290 kilos off the ground. And it's like, I don't even know how that's possible, Yeah. I'm doing half of that and taking everything I have. And even, if you do weightlifting, it's like, you think, if you add 10 kilos, it's not going to matter that much. But like every 10 kilos is kind of exponentially harder. And then adding, doubling your amount is crazy. So
yeah. I mean, being able to do like 10 reps and like 0 reps, I mean, that could be the difference in like 10 kilos.
Yeah, exactly. But no, and I think so. I like powerlifting as a sport also because it's so simple.
Yeah.
Like if you I remember as a kid, everyone would be training soccer. That was like the thing in Iceland at the time. And then they would go to soccer practice like 3 times a week, and then they talked about soccer. And then I tried to join soccer practice, and it's just so complicated. You have to hit the ball, you have to run, you have to know where to stand. You have to be able to. There's a lot of different things you have to know. Okay, but in powerlifting, it's just you just stand there with a lot of weight, and it's just just like with deadlifting, you just pick it up. pick it up.
Just lift the thing.
Just pick it up, you know? And there's a few rules on like how you're allowed to hold and stand and whatever, but it's like, if you manage to pick it up and you didn't do anything weird, it's like, it's fine. You know?
Yeah, you got it. Like, you know, it's as long as you can pick it up, you're done.
Yeah. So for me, it's a very kind of meditative type of sport, right? Where you just you go in and you work, you know, you train for years and you just the same lifts again and again, just slightly higher. And I think the other thing that's interesting is that the sport itself is not really about the competition, in the sense that you know, you go there, you go in one day, you know, every 3 months, and then you pick something up, and that's, you know, where you stand right now. But the real competition is just, you know, showing up to training, eating correctly, sleeping correctly, and like just kind of the discipline that you need to kind of keep training and as well as you have, and like not plateau, right? And I think and that also is one thing I enjoy, right? In the sense that like if you and then you go in there and you go 3 months later and then you can't pick up as heavy things anymore, and it's like you've clearly your performance is clearly lower, right? Whereas you know, in programming, it's like if you're not writing the same code again, right? There's no way for you to kind of check exactly where you stand today on programming skills, right? Whereas in lifting, it's like like there's a number. If you can pick it up, then you know exactly where you stand, right? So
it's very egalitarian, like, or you what do you call it? Like, it's like, you know, the you get what you put in, sort of.
Yeah, exactly. I mean, and then, you know, and then a lot of it comes down to also just genetics, right? Some people are just way better at building muscle. And I think also for deadlifting especially, there's like the shape of your body really matters. Like if you have long arms and short legs, that's really good because you have like a better, you know, you don't have to reach down as far, basically.
So something that's like, you know, if you're sort of shaped kind of like a gorilla, then you should might consider getting into like powerlifting.
Exactly. I think that's the meme. It's that the orangutans, they have peak powerlifting physiognomy, right? Because they have the, you know, but still, you know, the people who are the best in the world, they're normally shaped. So, you know, I think if you train, you can get quite far no matter how you're shaped, but you just have to vary your technique a bit.
Yeah, I see. So, how did you get into this, like the deadlift thing? Like you had your friend, but was that like
no? I think so. There's this very influential book called Starting Strength, and it just teaches you how to deadlift, squat, bench press, and then they do overhead press as well. And it's just. And then, you know, and the focus is like, you know, I think the first time I went to the gym, I was doing a lot with some friends who were very into it. And then I bought like Arnold Schwarzenegger's book on bodybuilding, which is, you know, it's considered the Bible of bodybuilding. And it has like 300 exercises, you know, to target exactly this muscle on your inner thigh, you know. And it was just wait. And then I tried to do that. I assembled some program and then I tried to do that for a while, but it just gets very overwhelming in a while, right? So then I stopped going to the gym. And then when I came back, I thought, okay, I'll just keep it simple. So I got this Starting Strength book, and in there it's just 4 exercises. And I mean, and these are also the exercises you compete in powerlifting. Or I mean, I think they stopped competing in overhead press now, but. And then you just do them. You know, you just go in. You're there for like 40 minutes. You do these exercises, and then you go home, right? You're not thinking about, you're not waiting for the machines or whatever. It's just you, and it's also just barbell exercises, right? So it's just, you just need to find a rack, and that's it. And then you just go in, go home. And then it made it a lot easier to just come in, you know, every other day, because I knew exactly what I was going to do. I was not thinking, oh, I'll do this for 3 days, or like, is it leg day today, or like, There's no variation. It was just the same thing again.
Yeah.
It made it easy to be consistent.
I guess it's more like I remember from have you seen that documentary, the Pumping Iron one with Arnold? Yes. You can sort of understand, like, because he's sort of like Michelangelo sculpting his own body, sort of like in a way. It's like, the balance is a bit off here now. I need to target this muscle right here. Of course, like, then you might need like a very, very specific exercise. But starting strength is a great book. I've also used it from time to time.
And I think just with people like Arnold, it's like they have no idea what normal people are. They don't. They just assume, I'll just make them do 15 different exercises. That's not a lot, because I'm doing 300, right? So this is very little.
Yeah, back to basics. Just like the 30 essential.
Yeah, exactly. So I think, and I think it's very usual in like every field. It's like you assume that just normal people, have some capacity to very quickly adapt to what you consider the minimum, because that's and I think because that's the minimum is determined by the point that you start listening to people, right? So they haven't reached that yet, then you don't listen to them, right? So they're not on your radar, because you literally don't know anyone who's a programmer that doesn't know at least Python and maybe JavaScript and also HTML, right? Like, where, the vast majority of programmers, they just use Excel. They're not even aware that they're doing programming, right? But they're doing their equals sum and then some conditional cells, and then they're doing a bunch of programming, right? But they're not considered programmers because they don't consider themselves programmers, right? But it's and you're like, would you listen to them about package, if they said, I have this opinion on package managers, and they're like, you use Excel, like you just install it from Microsoft, you don't know. So it's like, I feel like you need a certain level of having had to deal with a bunch of, bad tools to be able to kind of have an opinion on tooling, I guess.
And I guess also, like you said, it's like if you're like a complete and absolute beginner, it's like, it's not even that you don't, there's a bunch of things you don't know. You don't even know what you don't know, so to speak. Like, you don't even know what question to ask, I guess.
Yeah, I think, it's not that beginners, like, I really like their excitement, right? They're really ready to learn and they're really happy, but they're like, they're often young, I want to say. In the sense that, like, I feel like I'm still young, but they will have very strong opinions about something, right? And and my first instinct is always to believe people. I'm just naive like that. And then I go check out whatever they're pitching, and I'm like, this is crap. I don't. Why do you? And then I kind of remember. Oh yeah, they don't know what they're talking about, right? Because it might seem cool, but then you really look into it and it's like, okay, there's a bunch of problems here. So
yeah, but did you used to be like that as well? Do you remember, or?
Yeah, I mean that's how I grew up, in the sense of I've always been kind of the person having very strong, like, I used to have very strong opinions on everything. And then that's included like operating systems and editors and programming languages and stuff like that. But then I kind of, I learned about other things, and also just learned that, it's not, you really have to think about the user as well, right? Like, and the users are all different, right? So what might work really well for me might not work for you. And then it's very naive to be like, if you don't have a modal editor with Vim key bindings, what are you even doing? And it's like, well, some
you're
people,
not gonna make it.
Yeah, exactly. You're not gonna make it. You're not gonna make it. But then some people just like clicking around with their mouse. They'll go click, click. And I do make fun of them, but I respect their choices.
Yeah. I think as well as like as you get older, more experience, you sort of start to realize that like there's things are always more complex than they appear. Like usually the answer to any given question is not like what exclusively, but also like whom and why. Like for someone, Emacs might be the ultimate editor, like for them and their use case and their current skill level, etc. But
I think it also just comes with having seen a bunch of hype cycles, right? Like, you've been there when Emacs or Neo Vim came out. It was like, oh, this is so great. And then the hype died down, and you're like, oh, there are some problems. And then you see the new thing come out, and you're like, and then you kind of remember. I remember when I was like this, and I was very interested in some editor, and it was like, it didn't work out. Like it seemed very cool at the time, and then it didn't work out. And once you've had this happen 15 or 20 times, you're like, a new editor comes along, and you're like, there's something wrong with it. There is going to be something wrong with it that we just haven't realized yet, right? So.
And also it might not actually be worth the like time you need to invest, possibly.
Yeah.
Like I don't know, to paraphrase Paul Morphy, like I sometimes feel like knowing Vim is the sign of a gentleman, but knowing Vim well is a sign of a wasted life. And I'm saying this as a Vim user. It's like
and I think especially for me in the editor wars, like I've used Vim, I've used Emacs, I've used VS Code, I used like Notepad++ for a while, and then I've been bouncing around every now and then. And then I think, because for me what happens is that I like the editor, I like customizing it. I customize it too much, and it gets very slow. So just I'm adding too many features. Plugins. So then I'm like, and then I start some new editor, like, wow, it's so fast, but it doesn't do anything. Snappy. It just starts up right away. And then, for me, it's a continuous cycle of like, and then I go back to Vim, and I'm like, I'm going to write a great config this time. There's going to be no bloat. And then you get used to this kind of new editor feeling, right? It's like getting a new car. You're like, oh, I'm going to use Emacs this year. And then,
fresh start.
Yeah.
And this time it's going to be different. Like
yeah, exactly. Yeah.
Yeah. But speaking of like getting into things, how did you get into functional programming?
Well, that started out with one of my tools, actually. So I was using Arch Linux, by the way, at the time, which I later grew up. I realized that it's not worth my time to fight with Arch all the time.
Did you become a normie?
That's a funny thing. It's like I used to hate these people, like hate them, but now I'm like, oh, I get where you're coming from.
Yeah.
So I was using Arch, and then I was looking for a window manager. I tried for a while to be only in the terminal, okay? And I don't mean like in the terminal emulator. I mean like I didn't have any window manager or anything. I booted up into TTY, and it was like, and it was really bad. There's nothing you can't browse the internet in TTY. Like there's like an Emacs browser that you can kind of use to see, but it doesn't run JavaScript. And it's like, it was a very terrible experience. But it's a learning experience. And then I was like, okay, how can I find the most minimal window manager to suit my purposes? And then that's when I ended up installing Xmonad, which is this modal editor. Like it's a tiling window editor written in Haskell. And I think, and the Xmonad is basically just bindings to X, right? So you boot up X server, and then you can control the windows or whatever with this Haskell thing. And it was like extremely configurable, right? Because it's just you're just writing raw combinators of X operations, right? So you can kind of do whatever you want. And that's why I used to have this huge Xmonad config. Like I said, I always configure things too much. And that's how I kind of started to get familiar with Haskell. And then, I think as many people do. I ended up taking a class in university on programming languages, or like, yeah, it was just called programming languages. And then we did some Scheme, we did some it was a language called Morpho, which is like, it's like the professor there made this language called Morpho, and it has a very interesting like module system. It's kind of like the ML module system, but it came before that. So it was kind of like, you wouldn't define any operations. You would like import plus from this module, and then that's your.
Okay.
So everything was bound. So it's like I think his research was on module systems or something like that. And then of course we did some Haskell as well. And then it was just so nice, right? Because I was used to, in my other courses we've been using Java. We used C a little bit, but it was mostly in Java, and it was just so like you just had to write so much, like you know, literal.
Very verbose.
You have to push your keyboard a lot of times, right? To just write. I mean, now I think you can get away with a lot of autocomplete and vibe coding and whatever, but like at the time you just had to write a lot. And then, you know, Haskell came along, and you saw all these elegant kind of one-line solutions to everything you ever wanted, right? And then I was using Python a lot as well. So I think my first entry into programming was Python. I had a summer job at a pool, and I was sitting in the reception, and like nobody comes to the pool in the middle of the day. So I was just reading books on how to program in Python.
So you had time to kill.
Yeah, exactly. And I was always a nerd, right? So I thought programming was cool, but I didn't know. I think it was cool, better to be in the UK, like in the 80s, when everyone had these small, I think they were called the BBCs, or like what then, you know, what the Raspberry Pis were inspired by. Like everyone just had these home computers, and you kind of had to program them, and a lot of people got into programming that way. But by you know, our time, I want to say, like in the early 2000s, it had become a lot harder to program your computer, right? So the only way you could do it was you could kind of, you had Python, and then you had this idle editor that came with Python, right? Because I didn't know how to use the command line. Yeah. And I would play around with some programs.
But that's true actually, because like I remember in the olden days when you would like boot into DOS, like those, usually you had some kind of like basic dialect installed, so you could just like, you know, type a command and it would launch like a basic editor. I think we've kind of lost that, like you said.
Yeah, and I think as you know, kids these days, I've noticed, because I was teaching at the university, and it's just, you know, the concept of the file system is moving further and further away from the kids, right? Because they use apps almost exclusively. Like most of their computer use is like iPads and tablets and phones and whatever. So I remember like teaching databases, and it would be like they would very often have the issue that they were not in the right directory. And then you would have to be like, oh, you're not in the right directory. And they're like, oh, yeah, directories exist, right? Like, you kind of see the, and then for, you know, if you're my age, it's more like, that was how you program things, right? Or like you had to click into my computer and then go into the C drive, and then you had to you always had to navigate your whole file structure to do anything. Anyway, so I ended up doing Haskell at university, and I just fell in love with how elegant it was. And then I wanted to read more, like learn more about it, I guess. Because I was always tired of the whole Java. You know, Java was cool, and I think Java is it is a very good language for enterprise, right? It's a very good language for like a lot of programmers to collaborate on something together. But I feel like if you're teaching it at like intro programming courses, you know, if you're teaching like algorithms with like Java arrays, it's just not it's not the level of abstraction you want to be on. Right?
No.
Like you either want to be very high, as in Haskell, or something easy to read, like in Python. I think Java is kind of bringing along a lot of enterprise stuff that
Yeah.
you're anyway going to have to relearn when you do the job, because they're going to have to teach you how they do it.
Yeah, like I remember actually, like we had when I took an intro programming class at university, it was in Java, and basically, like, you know, pretty much the first thing the lecturer said is like, okay, now I'm gonna show you a Java program. Don't mind that, like static void main stuff. Like, you know, we'll get to that later. And I mean, that just goes to show, like, you know, I mean, it's not really a great teaching language.
No, and I think, I mean, and it was never designed to be a teaching language, right? But then people think that to get a job, you have to, like, be taught in the language that you're going to work in, which I think is, I don't think it's, you know, I don't think it's actually true, right? I think if you get a good enough grasp of programming, you can pick up basically any. Let's say, you know, if you learn a language from each dialect, you can kind of, like, if you know Python very well, you can go to Java in a month, right? Like, yeah, you won't be able to solve your coworkers, you know, package installation issues because you've seen it before, but like you're able to be productive right away. And I think that's why I think, like, teaching, you should really use languages like Python, or even languages like Haskell. I mean, I'm slightly biased, but like just to get people used to the idea of programming, and also, you know, once you learn something like Haskell, you realize what it is that you're doing when you are writing Java programs, right? You realize that, like, okay, every single line that you execute has a side effect. And then you're creating these objects and passing them around, and then that's how you're managing state and stuff like that. Whereas people, like, I think if you're only exposed to that dialect, you don't get this grasp of kind of what it means to write in an imperative style, right? Because you never see anything else, right? So I think, and I think this can happen often. Like, you don't understand your own society if you never travel. Right, you don't.
Yeah, that's a good point.
You have to really experience another world to see your current world more clearly, right? But, you know, most people just learn Java, and then they go to the job market, and then they're like, "Do you know C++?" And they're like, "Yeah, sure." And then you learn it. You know, you pick it up, right? So yeah. No, anyway, so I studied this one course in Haskell, and I thought, oh, Haskell is the best. I want to do more Haskell. And then I came here to Sweden, to the bastion of functional programming at Chalmers.
Yes.
Where they have, you know, they had all these legends, like John Hughes and Mary Sheeran, and Leonard used to be here. And it's like it is really embedded into, like, the Haskell memosphere, right? Yeah. So people know of Chalmers, and I've been reading papers coming out from Chalmers as well. So in order to come to Chalmers, I did I think a 2-year master's in programming and algorithms or something like that. But I think I did it in 3 years, actually, because I was working full time as well. So I was working at this startup where we were doing, like, a social network.
Oh, really?
You know, and you've never heard of it, because it's so, you know, the whole backend was like in Python, in Django, and then it's really funny that, like, it was in 2015, and we were using, like, Django, we were using GraphQL, and we were using React, and this is the exact same things people are using now 10 years later, right? And these were all brand new, like, by the time. So we were really, like, at the cutting edge.
Yeah, cutting edge technology.
At the time, but now it's kind of like, yeah, everyone uses React.
Yeah.
So it was a fun time to be in web development, but, you know, but I got kind of, I want to say, jaded by the startup industry, in the sense that, like, you know, you work really hard and you put a lot of effort into something. And I mean, you get paid, right? But then, you know, if it doesn't go anywhere, it feels like you've kind of wasted your time, you know. And then so that happened. So that company, it didn't go bankrupt. It, like, went defunct, right? So they stopped. I mean, they didn't have money. I won't say we didn't have money for salaries or anything, so we just kind of shut it down. And then and the main problem wasn't like, I think the back end was good, the front end was great, but the real problem was just like to launch a social network, you really need like a big mass of people to start using it, right?
Yeah.
And I think we didn't know how to do that, right? So
yeah, starting with like a social network that feels like doing startups on like hard mode, because it's like that classic chicken and egg problem. Like
yeah, I mean, I think it's also I think the movie The Social Network came out in like 2009, right, or something like that. So then, like, people had seen that movie and they're like, "Oh yeah, making a new social network. That's a great idea."
yeah,
But
yeah.
no, but so that was a lot of fun, and I got a lot of experience in being like a full stack developer, in the sense that, because it was this company. I mean, we got more employees later, but in the beginning it was just me, right? And it's just like there's some business guy, and he's like, "I want a social network," and I'm like, "All right, how are we gonna do that?" Right? So you have to really learn the whole, like, we were launching machines on Amazon, we were managing the database, we were writing the back end, and then also the front end, and then until we got more front end people. But I think it was really fun to, it's really, I think that's what I like the most about startups, is that you really get to experience the full world of programming, right? Like, and also, like, you can't just be like, "Oh, the database people, they won't let me do this." It's like, you are the database people.
You are the database people.
So, and then also, like, if the database doesn't work, it's your fault, right? So you have to, I mean, you get a lot of experience with everything. But then, yeah.
I think another thing that's super valuable, and I've just like just to interject, I've been part of a number of startups in my career, and I love it. I love the the chaos and the camaraderie, and like sort of you have to be sort of like, I don't know, it's not for everyone, I guess, because it can be quite stressful. But I think one thing that's super valuable as well is you get a really good sense of like doing cost benefit analysis of every solution.
Right.
Because I think that's easy. Like if you're used to working in big enterprises, it's like, it's easy to think of yourself as someone whose job it is to write code. And I mean, that's usually even in the job description. But I mean, every programmer is employed to sort of generate value for the company.
Yeah.
And that becomes very clear when you're in a startup and, you have an important demo or an important launch, and the things, you have to get things done. Like it sort of cures you of your perfectionism really quickly.
Yeah, for sure. And also, I think to pivot back to Haskell, that really made me appreciate, why we have like testing and type checking, right? Like the whole point of that is to, because this was all in Python, right? And then there was no MyPy at the time, so there was no type checking, and then like the only way you knew something crashed is because the boss tried to do something and it didn't work, and then you have to go into the runtime logs, and there's going to be like this type error in your runtime logs, which you very well could have found at compile time, but there's no compiler, right? So.
Yeah, I feel like I have to mention that Godfather meme you posted on Twitter.
Yeah.
It's like a picture from the Godfather. It says like, "You come to me at runtime to tell me that your program doesn't compile," or something like that.
yeah, exactly. No, I think it's it's valuable. It makes you go very fast, but I think what we've seen since then is that Python has added these type annotations, and now you can type check Python, right? And I think TypeScript came out around this time in like 2015. So just to add types to JavaScript, right? And then all the big enterprise companies, they're all insisting on like we write things in TypeScript, right?
Yeah.
Because we want the guarantee that like it's gonna work in some sense. So, and I think that's what kind of drew me to Haskell
It sort of reinforced your belief that you were onto something, or
Yeah, I think like the idea with Haskell also, it's positioned in a very interesting way. It's that there's something called the lambda cube, right, which you have these different type systems, and the current one in Haskell is called System FC. And I don't know the lambda cube myself, right? But I know it exists, and I know that you can kind of choose points on this lambda cube. So you have different type system features, but then you're sacrificing something else. And then the choice that Haskell has made is to be like the most powerful type system you can be without sacrificing inference, right? So if you go to go to a language like Agda or something, which is fully dependent type, you can express basically anything in the types, right? I don't think you can do I/O, but like the part of your specific, like when you write your specification of the program in the types, you can do whatever. You can be like, I'm going to check the type value of this thing that's going to be passed to me at runtime, and then I'm going to use that to kind of branch into different types. Which is very cool, right? And you can really do, proper mathematical proofs in dependent types. Whereas in Haskell, but the thing is, if you have these fully dependent types, is that you sacrifice inference, right?
Yeah, you have to annotate all the top level functions at least.
Yeah, and like you have to just do a lot of annotation because it becomes undecidable, right? Like you can't infer the type of the program, and it's like, becomes this halting problem, right? But Haskell made this choice kind of to be in that position where you can infer almost everything, right? You don't really have to give any types to any functions, but except, of course, as time has moved on, we've made some concessions in the sense that I think it was originally written in System F, and now it's in System FC, which has these type class constraints, right? And they allow, and then, so usually when you have to add a type annotation in Haskell, it's because there's some type constraint, like type equality constraint going on, which cannot be automatically inferred in many cases.
Yeah, it's like I know you can end up with like like a case where the type ends up being ambiguous, right? And then you have to sort of resolve that.
Yeah, exactly. And then so and that for me was the very interesting part, in the sense that like at every point of your program you can infer the type, right? So you can know exactly what type every single identifier in your program has at that point, right? Even though they could be very general, right? Like you could say this could be any foldable type, or any kind of list or anything you can map over or whatever. But at that point in the code, you've either inferred that it's still general enough to be considered a foldable, or you've inferred that you need a more specific type than that. Which I think is so it's kind of type synthesis, right? Where you inferring the type from the program. And I think that's
very
kind
cool.
I think that's a very important, for the usability of complex types, you have to be able to infer them easily, right? Otherwise you end up in, like, if you've seen languages like Coq, which is also dependently typed, it's just a mess. Like, you just have to annotate everything, and like, it's just because I can't read it probably, but like I have no idea what's going on at any point.
But it is kind of cool. Like I think one reason people usually are like have a negative reaction to the idea of static types is that they think of it as having to do a lot of manual bookkeeping, like basically a lot of double entry bookkeeping. Like, why should I need to type the type of this function, etc. But in Haskell and a bunch of other like ML languages, usually you don't have to write down any types at all.
Yeah,
I mean,
exactly.
That might not necessarily be a good idea. Like, it's still valid use cases for annotating functions and such. But it's like like you said, a lot of the times you don't have to.
Right, and I think it's also I mean, it's also very valuable as kind of documentation, right? And there you can do all these kind of new type tricks where you can kind of say, oh, this type here is going to be the username, and then I'm just going to represent that as text, and then you know from the type that it's supposed to be the username, and you otherwise. I remember this meme from a long time back. You know, the guy with the bicycle and he has like a stick, and then he stabs the sticks and falls over. You know, people will be like, types are really good, and then they have a function that's like string to string to string to string to string, and then it's like, it's not telling you anything.
Yeah.
Right? Whereas, you know, you can model your types in such a way that you kind of annotate your type. So you say, okay, this is the username, this is the password, and then you can even make sure that I'm never gonna release the password, or you can make, you know, you can do a bunch of very cool things in the type system as well, using something called phantom types, right?
Oh yeah,
which are kind of these extra parameters that don't do anything at runtime, but they just that you annotate your program, and then you can kind of infer, okay, what is the size of this data set, or like what is the you know. And you have all these things like you know, you have graded like monads, and then you have like these graded monads that kind of allow you to in like while you're doing your imperative function, the types can kind of add up and tell you like, for example, the complexity of your program, right? So you can kind of automatically infer the runtime complexity of your program by just, you know, very complicated types, but still kind of expressible in Haskell, which I think is very cool. So that's what I like about Haskell is that you can just keep it very simple, int to int, and then you can also go very complicated and model all these things in the types, and then all these things live together in the same ecosystem, so you don't kind of have to worry about it too much.
Yeah.
But it does get painful when things don't type, right? And then it would be like. Unapp, you know, because I'm working with a servant now, which is this typed web server thing, and you know the errors are like unapp, uncontext, and then like a huge message could not, you know, expected this, and then actually was this, and then it's like, because it doesn't do renaming at the error time, right? So it gets very messy. Like the error messages get very messy, and I think that's what. The worst part for beginners with Haskell.
Yeah, pages and pages, and like, you know, I'm still not good enough at Haskell to like be able to parse error messages fast. It's like, you know.
All right. I mean, yeah, they're telling you exactly what went wrong.
Yes.
Right? But they're not telling you how to fix it, and I think that's one problem for us.
Yeah. But speaking of like fixing and stuff, I mean, you went on to get a PhD, right?
Yes. I was tired of the startup life. You know, putting a lot of effort into something, it didn't work out. Then putting a lot of effort into something else, it didn't work out. So I wanted some more stability, and I thought, if I do a PhD, you get like 5 years of stable salary, and then you get a PhD at the end, which is great.
Yeah, as an added bonus.
Exactly. So that was for me, and you know, I also so I wasn't really interested in research. When I start, like when I, you know, it wasn't like, oh, I want to do a bunch of research. It was more like, I think it's a nice thing to do now. I'm tired of the startup life. But then I really got into research afterwards. But I've always been very practical in the sense that, like, you know, if I'm doing something, I really want to be able to run it, right? To just kind of get a feeling for it and understand it. Which can make it difficult when you're writing papers, because you're like, you have a system, it works, and then you would like to add all these other things to make it like actually usable, like by normal people. But you end up not being able to do that because you don't have the time to do that, because you need to produce more papers. So, so I ended up doing a PhD in program synthesis. So the way it started was that I was doing my master thesis actually. And I was doing this, I mentioned these graded monads before. So I was trying to do, so we have one professor at Chalmers called Mary Sheeran, and she does a lot of like circuits Okay.
Oh, okay.
So she she has this lava thing and Kansas lava, where you write Haskell programs and they get compiled into FPGA circuits, which is very cool. What I wanted to do is I wanted to automatically determine the size of the circuit, like by tracking it in the types. And it was kind of possible, but you ended up with something. The error message would be like, could not unite true with false. Like, that's good, but it's not really helpful. And then what became really difficult is just to figure out exactly what to write, like how to write these programs. So then I started doing these typed whole things, right? So I think they recently been introduced to GHC at the time. It was like in 7.8 or something. And typed holes are these things where they're sometimes called contexts also. So they're kind of like a hole in the program. And then you kind of infer the type of that hole by all the functions that are around the hole. And it gives you like the most general type of thing you could put in there, and the program will still compile, right? You can put more specific things that would kind of refine the type, but so it infers the type of the hole, and it also gives you some context information, right? And this has been used in Agda a lot for like, you write Agda and then you have these typed holes and then you kind of automatically fill in the holes and then it expands and then you have more holes and stuff like that. And then what I wanted to do was like, okay, now I have these typed holes. I can figure out the type of this thing. But what if we just figure out what to put into the hole, right?
Okay, so just to go back a little bit, like, so a typed hole is kind of like a placeholder that you can put anywhere in the program.
Yes, anywhere at the value level on the right hand side of it's completely like exactly where you can put them is basically everywhere. Yeah. But not on the left hand side of an equal sign, it means something else. But on the right hand side, it means it means typed hole. Yeah. Like this value level typed hole. Yeah. Right.
So you can basically say like, I don't know what to put here, so I'm gonna leave this blank, and then sort of the type checker sort of infers what you need, like what kind of type you need to put there for the program to compile, and then the program also keeps compiling, right?
Yeah. So it doesn't. I mean, it doesn't. These are complicated because I know too much about the implementation. But like so what happens is that there's a typed hole in your program, and so in Haskell, programs are compiled at the module level, right? So you compile each module at once, and then what happens is that you have the hole, and then you're doing the type checking, and in Haskell, the type checker is a constraint-based type checker. So basically, you have the context of the hole, and it's called emitting. You kind of throw up a bunch of constraints, saying I need something that fits this thing, and then what happens is that when you try solving all the constraints with a constraint solver, and then if you have any unsolved constraints, that's going to generate a type error, right? And that's where you get like mismatches between int and string, because you had a constraint saying this int should be this string, and you couldn't solve that constraint. Yeah. That's how you end up generating these error messages. And with typed holes, instead of just throwing away that message and saying it doesn't compile, you print out, here's what I figured out so far about this specific place. So here's all the constraints that are relevant to that place. And then what happens is that you generate an error message. So the error message is basically taking the unsolved constraints and generate error messages from those constraints. And that's the point where you generate the error about the typed hole itself, right? So you keep compiling. So you compile the module itself and everything else in the program that's not, and then you get information about all the typed holes that you found at the end of the compiling of the module, right? So you have one program, it's just when you compile it. But if you are doing it in compile, right, it will compile all the rest of the programs and things that don't depend on that module. But it won't continue after that module.
Oh, I see, I see.
Well,
and then you wanted to
yeah.
take this to the next step, like go
Yes.
beyond just saying like, oh, please tell me what kind of value I need to put here for the program to
Exactly.
compile.
Yeah, so I thought, okay, because we have all these constraints. We know exactly what the type of the hole is. Why don't we just tell you what you could put there? You know, like, it's kind of like autocomplete, you know, but for Java, you have these objects and then you can kind of look up into the object, like what fields does it have? But here we have like, here's everything in scope
Yeah.
that actually, if you put it in the hole, it would type check, right? And the way we do this is very naive. It's just you figure out everything in scope, like all the global things that you've imported, things that you've defined locally, and then things like arguments to the function, and then you just check. You just run the type checker on every single of those types, try to match it with the type of the hole, and then for those that work, you say, okay, this one would work, and here's how the constraints would work out. Otherwise, you just you don't say anything. And then, you get this list of valid hole fits that tell you, so it's kind of like autocomplete on steroids, right? So you can just kind of say, and now even in Vim or like with a language server protocol, you can kind of put your mouse over the hole and then just say complete the hole, and it will give you the list of options. And,
Oh, that's really cool.
Yeah.
So imagine I have a bunch of arguments, or I have a bunch of variables in scope, like maybe function arguments or whatever, and then like as I'm typing, it can say like oh, you're using a function that expects a list, and you just happen to have this list of this correct type in scope, and then it can just I can get like an autocomplete for that.
Yeah, exactly. So it really. So one of my interests is the tooling, right? Like how can we use all this information that's already there in the program, right? You'll have all the types, and then you have holes where people don't know what to write. Why can't we just use the information that the compiler has to make that task easier for the person that's writing the code? And I think that's it ended up being quite cool.
Okay, so this technique is like it's called like finding a hole fit, something that fits in, or
yeah, it's just called program synthesis.
Yeah,
because you're just synthesizing a program that has the correct type. Here you're synthesizing a single identifier. I also introduced something called refinement hole fits, which kind of they are hole fits, but they're expressions that have additional holes in them, right? So you kind of say, I didn't find anything that fit the hole exactly, but if you have, the map function and you apply it to two things, that could work as well, or something like that, right? So you can kind of, and then you can imagine it kind of recursively filling those holes in, and then you would eventually, you could come up with any expression.
Okay, yeah, that's cool. So basically, you're saying that like, okay, there's nothing that fits the hole, but there is using this function, you could turn this value into something that fits in the hole. Is that the idea? Okay.
Exactly. So you kind of, I don't have anything, one thing, but I have a function that does take, like that if you give it the correct thing, it would return something that works. And then you can kind of just try and figure out, and that's kind of how Agda does it, right? You kind of can expand a hole into some new holes, right? So.
Yeah, so if you want to play around with this, like how can you do it? Like, is this available as a GHC plugin, or?
No, it's just in GHC itself. You just write a hole. You just write an underscore. Like if you have Haskell code and you write an underscore and you compile it with GHC that's newer than like 8.6, which was 2018. So you should definitely have something newer than that, and then it will just spit out these valid hole fits. And then there are some flags like, set whole like refinement level, which gives you the these refinement hole fits as well. And it just works, right? And I think even if you have your VS Code or language server like Helix or whatever that supports the language server, then you can just write a hole anywhere in your Haskell code, and it should offer up something called an LSP code action. And the Haskell LSPs, uses the valid hole fits to generate those those actions. Right?
Oh.
So
Yeah, I've never tried this actually. Like I've been typing out things by hand, like a primitive.
it's a rookie mistake.
Yeah.
Actually. Yeah, and just to tie it back to, this is what I didn't like about Java. Right, I have to write everything myself, and now, so I figured out how to make the computer do that. No, it's quite. And I use it a lot myself, right? And I think that's the real measure of a feature, right? Like, do you use it?
Like dog fooding. Like, is it?
Yeah, exactly.
Is it
I
actually
think,
usable?
And it's one of those things that are like, they're not theoretically hard, right? There's no type theory behind it, but a lot of people found it very useful right away, right? Which I was very happy about. So.
And did you contribute to or did you build what features did you build in this? Like, what was your part in the?
So I extended GHC and added, so like when you generate error messages for hole fits, now you generate. When you generate error messages for typed holes, you also generate these valid hole fits.
Oh, okay.
So I added that, and then I added these refinement hole fits, and then because one of the tricky things about this is like, how are you going to sort the list? So you have a bunch of hole fits, and are you just going to report them alphabetically, or do we want to do something smarter? So then I did some work on like. So there's two ways to go about it, and that you have in GHC now. One is called subsumption sorting, and it's this idea of like the most specific one should be the first one. So that kind of narrows the type down the most.
Oh yeah.
And then you can have like the most general one at the end. So stuff like undefined or error. I think we actually filtered those out, but like things that like very general types, they're probably not what you're looking for. If you have something that has exactly that type in scope, then we'd rather use those. So those are sorted first, and then it doesn't matter if you have like 5 things, but you have like 30 things. We only display the top 5 things, right? So it becomes really important to sort this list nicely. So the subsumption sorting is like, it checks everything against each other to kind of build this graph of how everything is related, and then just prints out according to that order. But the way we do now is, I think we count constructor distance, which I think is, so you count the number of constructors in the type application that you would have to apply to make this new function fit the type of the hole, and that lets you, and it's much faster because you kind of know the type application already, so you just count that, and then and then you can sort it really fast.
Okay, so it's almost like Levenstein distance, but for okay, wow, that's really really cool. But how did this come about? Like, did you start this work as part of your PhD, or what?
No, this was just my master thesis.
Okay, so wow, we're only at the masters.
Yes. So I was doing this program synthesis, and I wanted to continue with that. And then I started my PhD, and then I was doing these, just continuing with program synthesis. I did my thesis with Dave Sands, he's called. He does mostly security now, but in the past he's been doing something called computing with contexts, which are kind of like the theoretical type tones. They're slightly different. I keep thinking they're exactly the same, but he keeps telling me that they're not at all the same. So, and he's probably right. So, so what I ended up doing in my PhD, I ended up taking this idea. I did some weird stuff first, something called weak runtime irrelevant typing, where it has to do with these phantom types, where you can kind of you can add a mode, like a compiler plugin to so So you can add a compiler plugin that allows you to how to say this well. So imagine you're writing a program and you have all these phantom types. So you have like a program and you have some security types on top of it, right? You want to say this value has high security and this context is low security. And then you don't want to leak high security information into a low security context.
Okay.
It's called information flow control. And then you can annotate all your Haskell values with these things. But what ends up happening is that at runtime, you don't, it doesn't matter. Like all the phantom types are erased, right? So they don't matter at runtime. But what can be problematic is testing these things, right? Because you don't know how to, like you can't run the program unless the security types are correct. But maybe you want to test them before you figured out exactly how your security type should be. So
because you sort of want to test like the, what would you call it, like the negative case.
Or just the functional behavior and not the, you figure out the context later.
So like what happens if a user tries to do something that's illegal, for example?
Yeah, kind of, or like it just erases all the security things, right? So you might have a secure sorting function, but then you want to test it if it sorts, right? And it doesn't have anything to do with security. So what this plugin allowed you to do is it allowed you to kind of forget. So it allowed you to kind of, in the types, forget about the security so that you could run it normally. And that was kind of cool. And then I expanded that into this plugin called the Dynamic Haskell plugin, which automatically makes your programs into dynamically typed, basically. So you kind of have dynamically typed lists, and you didn't have to have these. So in Haskell, you have dynamic types, but they use these from-din and to-din constructors. And it would just kind of add those where appropriate. So you can kind of have Python-like lists with like a...
You came full circle. You
exactly.
realized, Python, it wasn't so bad after all.
Yeah, no, I thought it was quite funny. No, and then so I was basically messing around for 2 years, and then I did this thing called Proper, which is this property-based program repair program. Okay, so how did that come about? So I was writing a program synthesizer, in the sense that I'd been. Okay, so let me backtrack a little bit. So in the middle of this, I did something called typed hole plugins, right, for GHC. So I added that to GHC, that you can now add compiler plugins that deal with typed holes. And it was exactly for that reason where, like, I had some ideas on how to sort the functions, but I didn't want that to be the choice, right? So you could have these plugins that allow you to remove candidates, to add candidates, and to reorder the candidates. So you can kind of customize how your typed hole fits worked. So and then what I did is I did this proper thing where we did this loop of, like, you would have some tests. We figure out what parts of your Haskell program those tests are referring to, and then we run the tests, and then we find out so which would, in the tests that fail, exactly which parts of your program was involved. And then what we did is that we did this synthesis where we just replaced all of those locations with typed holes. And then we synthesized new fits for those typed holes. And then we tried to test it again, basically. And then we had some genetic algorithm that kind of combined different hole fits or different solutions together. And then just ran this in a loop, and it would kind of automatically be able to repair your Haskell programs, right?
Oh, very cool. So it's like, and a broken Haskell program was one that failed the test, for example.
Yeah.
And then it can go in and like automatically fix your program.
Exactly. So you just kind of handed a module that has some tests and that they don't work. And that got into ICSE, which is this software engineering conference. And I think they were mostly impressed by Haskell. Like, they were not really impressed by, because in the paper we were talking about using property-based testing and how that was better. But they were just impressed that we were able to do all these program repair things without having to write so much of code, basically, right? Because we had all these, because if you do program repair in Java, what you might do is you might change one part of the program, but because you have side effects everywhere, it might change some other part of the program that was previously uninvolved. So you can do a lot of bad things accidentally, but in Haskell we don't have these issues. So we can kind of just take the program, run it, and just go wild. So that got in. They were very impressed by Haskell. And then I kind of kept working on program repair related things. So I had one paper on, it was this paper called Spectacular, where you would synthesize tests, or you synthesize properties, right? So there was another typed whole kind of thing where you would have, so the idea is basically synthesize programs where you have some free variables like x's and y's. They can be lists or whatever. And you're synthesizing them on each side of an equal sign, right? So you just want to find out things in your program, like combinations of things in your program that are equivalent to combinations of other things in your program, right? And I mean, so this was the Spectacular paper. It had been done before by Quick Spec, it's called. But we had these new things called ECTAs, which are these tree automata things that my co-author had invented, basically, or at least his thesis was on that. And it allowed you to do like really fast combination of programs, basically.
Okay, it's like generate the programs faster.
Yeah. So it would synthesize them from the type, and you give it the type and the different types of the things you wanted to use. And it was a lot faster than what the quick spec people had been doing. And I think the thing is that, like, once you combine, when you're combining expressions, they grow really fast. It's something called the Catalan numbers. So like for the example we had is that we had, I think 132 different identifiers or something like that. And then we were synthesizing expressions of size 5, meaning that we were using 5 of those identifiers. Okay? And if you work out the math, it's like 25 trillion different possible programs.
Oh,
right?
Okay. Yeah, that's a lot.
Because it's not just the way, because you're not just picking different things in different combinations. It's also like which part are you applying to which other part. So basically, like where you're going to put the parentheses. And that makes it blow up really fast. But we were able to, repair things of that size, or like synthesize properties for programs of that size that was faster than so the quick spec people couldn't do it because they ran out of memory. But our solution kind of worked. So, and I think that was a lot of fun. And then I think the rest of my PhD was kind of spent on something called fault localization, right? So, that's this other synthesis problem where you have a program that's broken, but you have to figure out which parts are broken, right? So you have a test that's failing, or you have a test suite, and some of the tests are failing, some of the tests are working, and you have to figure out which exact part of your program is broken. And we had a lot of fun with that, with figuring out, okay, how can you compile with like coverage, and then you run your tests, and then you see which part of the programs your test touched, and then you build like this huge array of test failures, and they're called spectrums. So it's called spectrum-based fault localization. And then we were doing all these things in Haskell, and then we had a lot of fun of kind of doing these software engineering kind of things, but in a language that usually is ignored by software engineers. So.
Okay, so and the principle behind this, is it that like a line of code that's involved in a lot of failing tests is like more suspect, or is that like the basic idea behind this? Or
yeah, it's so you have some algorithms or like formulas that you use where you count the number of failing tests it's involved in, like the total number of tests, total number of failing tests, total number of successful tests. How many was this one involved in? How many passing tests was it involved in, how many failing tests was it involved in, and then you have some suspiciousness score basically to try and figure out, okay, I had this one part of the one part of the program that's always involved in all the failing parts,
That's suspicious.
but it's never involved in the successful parts, so that's a very suspicious place, right?
Yeah.
So and then you do end up getting, it doesn't work that well. I think that's also the funny thing about research, is that you sometimes do something and then the result is just, it doesn't really work. So
yeah.
let's do something like, nobody else do this.
Yeah, but I guess that's a valuable insight as well, right? Like,
yeah, I mean, it is. It's just harder to publish because people want something. Wow, this is the solution.
Okay.
They don't want more problems.
Yeah.
So, and then I did one thing that's called CSI Haskell.
yeah, I was just going to ask about that. Like, what
Yeah,
is
that was my
CSI
favorite.
Haskell?
That was my favorite paper title, I think. So CSI Haskell was this thing kind of. So we were generating traces error traces, basically. Like when you execute a Haskell program, when it fails, you want to know what it was doing right before the program failed, right? And I think in most other languages you will have the call stack, but then in for us we also have something called the call stack, but it's not quite as useful for us as it is in other languages. I think it's just because the way we write programs is that we split things up more and stuff like that.
Yeah, and like yeah. I mean, I think every functional, like if you've worked a lot with monads, for example, or like
Right.
the call stack is usually not very helpful.
Yeah. But so what this thing did is that it kind of it tracked when you called a function, like when you started evaluating some value and when it finished evaluating, and then you could kind of track like what was the program doing right, like what were the locations it was looking at right before it crashed, right? And the thesis was that in Haskell, because it's a lazy language, you don't evaluate things until they're needed, right? So it's call by need. And then what happens is that, so it gets a bit complicated in the sense that, so let's say you're running a program, okay? You're generating a list, okay? And the function that you're writing does not accept empty lists. It's going to crash. But you haven't used the non-empty thing or whatever. You just wrote it in a comment. Do not call it with empty lists. It's going to crash.
Yeah.
Okay?
Like the head in the standard library, for example.
Yeah, exactly. Exactly like head. And then, you call head on a list, and what will happen is that it will tell you that head crashed, right? And it's going to tell you where head is located in the GHC baselib, because that's where the error came from. And it's going to tell you where in your program you called head, right? But probably the issue was not with head. The problem was that the list that you computed and called head on was empty when it shouldn't have been empty. So something occurred before head that went wrong. But because you finished evaluation of that list, it's no longer on the call stack, right? You've already thrown that context out. But with the CSI Haskell, you could kind of say, okay, right before this crash, I was calling head, and you just finished evaluating this list, and then you can actually see where the empty list came from, right? Where is this expression that generated the empty list? And then you can actually find out, okay, that's probably where I should try to fix the program. So this all goes back to the fault localization thing.
Yeah.
And it's called CSI Haskell because it was it's like crime scene investigation.
Exactly.
Someone gets murdered, and you want to figure out, what did they do? Who did they meet that day? Were they arguing with someone? And it was it's like a crime scene investigation.
Yeah.
And it was so funny because we cited a crime scene, like a criminal investigations paper in our paper. because to establish that this is what they do at crime scenes, you know.
Yeah, that makes sense.
And one of the reviewers got mad, and they were like, "Oh, you are bulking it up with citations." Within this age of too many, it was a joke, okay? We thought it was funny.
The person
thought it was
didn't get
relevant.
the joke.
No, but it's like sometimes you also sometimes you cite random things, like the sky is blue. You know, how are you gonna cite that? Well, you go to the dictionary, and then you have a bunch of weird citations. But that was my pet peeve. It's like, why? Just let me cite something relevant. You know, I'm not trying to bulk someone's crime scene investigator's citation count. I don't care about them, you know. Anyway.
Yeah, they thought you were like, on the payroll of big CSI academia.
Yeah, exactly. So, and then I think that was basically my thesis, kind of this proper thing, the fault localization thing. And then the idea is to eventually come out with proper 2.0, right? That does... that integrates all this fault localization stuff.
Okay, yeah, because they can kind of integrate, right?
Yeah, so you have faster type synthesis, you have better fault localization, stuff like that. But then, as I was finishing up, LLMs became really good at program repair, right? So that's kind of my new interest now, is just to figure out, okay, the LLMs are here, people are going to be using them a lot, right? And how can we use them with Haskell in the best way possible?
Yeah, because it's really interesting. Like all the things you have mentioned so far is like things that people use LLMs for right now. Like, like if you have a piece of code and there's a bunch of code missing, like the LLMs can kind of fill that in. But thanks to the power of Haskell, you could do this without LLMs. So.
Yeah.
But now, with combining Haskell and LLMs, is that how much power can you get?
Yeah. So, I talked about these typed hole plugins before, where you can kind of customize the behavior of typed holes and the verified hole fits in Haskell. And what I wrote this hole fit plugin that actually calls into LLMs, right? So you can call ChatGPT or your local LLM or something. And then you can give it some instructions. So you can be like, I want a function that, sorts a list and takes them, it drops every other element and then sorts the list or whatever. And then, the LLM can kind of do that, which is very cool. But it's like, so it was quite easy because all the infrastructure was already there, right? Because I'd already written type valid hole fits. I'd already written the hole fit plugin. So GHC had all the features ready, ready for LLMs, right? So now LLMs came along. You just wrote a hole fit plugin, just calls an LLM, and it just works. And it gives you a sense of magic again, right? Where you can kind of, we're not going to be writing Haskell anymore because we have LLMs, but like, wait, we can actually do much better than many other languages can do, in some sense.
Yeah, because that's an interesting point. Like, some people are saying now that, with the advent of with the advent of LLMs, like the choice of code, choice of programming language is not as important anymore. But it feels like maybe that's not really true because like you said, language like Haskell with strong static typing, it can sort of inform the LLM of what it did wrong. Or what's your take on this?
So I gave a talk about this recently at. Well, not at StoryHack, but something called the Haskell Ecosystem Workshop, which is that, so it was called Ghost in the Haskell, which is this joke on some 80s anime that nobody's seen, but I thought it was a funny title. I haven't even seen it myself. I just like the logo. It's like an iconic thing.
Oh, you didn't? I haven't seen them. Oh,
no, I think I've seen enough of it in references that I know exactly what happens.
Yeah, but I have to. It's good. You should see it. You should watch it.
Yeah. Definitely after the talk as well. No, and then so what I went into that talk was basically I told people about LLMs, and then I gave the case, why Haskell would be a great target for LLM synthesis, right? So it's like you mentioned, like we have the static typing, right? So you have this whole compiler and that does a lot of type inference, right? So this is what I talked about in the beginning, that Haskell picked this choice where you can infer as much as possible about your program, right? So we can have typing, and we have very strong types, but we also have automatic inference, right? So that's very important. So because then if something goes wrong, you can tell the LLM exactly what it did wrong. Like I was expecting, you gave me this type, but I was expecting this type. Here's the context. Here's the things that are relevant. And you can just dump that straight into the LLM and you can kind of try and fix it right away. Whereas I think in other languages, like if you've had a Java program crash, it's like 5 pages of like call stack. And there's like one needle in the middle that's kind of telling you where the actual bug was.
Yeah.
So I was writing some PySpark last week, and then it crashed, and then it was crashing with Java. It was fine. No, anyway, so you have the proper type systems that give you a lot of information about your code. We don't have any side effects by default. So they're kind of, if you do side effects in Haskell, you kind of have to do them in the IO monad, or, in some monad that wraps the IO monad. So you kind of have to be explicit. You have to say, here's where I'm having a side effect. And this enables something called local reasoning, in the sense that, like, to understand a Haskell program, so every Haskell program starts with a function that's kind of annotated with the interface to that function. You're going to say, here's what I'm going to call this function with. This is what it's going to return. You have a comment that says what that is. I mean, that most languages have that. But because there's no side effects, you're really saying, like, this is the universe, right? Like, you have these arguments. You're supposed to produce this output. And if you can't do side effects, there's nothing else. There's nothing else that can happen in this program except exactly what you write there. So we've seen LLMs kind of now, they're pushing this context link thing, right? So with Gemini, and I think with Claude now, you can have like 1 million tokens. Like, and I'm not exaggerating, but it's like literally 1 million tokens. And that's like 70,000 lines of code, But it's still like, the more tokens you feed it, the harder it is for the LLM to pay attention to what it's doing, right? So it's all about this, figuring out how to make it's like fault localization, right? Like, how do you figure out in this huge code base where the problem is, right? So then what happens is that, you can dump your entire code base and just say, fix it, and it kind of doesn't know what to do. But the fewer tokens you have, the less context you have, the more it can focus, right? And that's the idea, basically, that because Haskell has these no side effects, a very good type system, and it enables this local reasoning, then you should be able to have LLMs generate a very good Haskell code because it knows so much about it, and it doesn't have to think about anything else. And the last part is also just that Haskell is very, it's not very verbose. Right?
Oh, yeah, that's right.
You just don't have to generate as much code, right? So I think all these things come together. And there are other more esoteric languages out there, but Haskell is kind of the only, production-ready, industrially sized language that has all these features and is ready to go right when the LLMs are here, right? So, and I think, people have said, back in 2022, the GPTs were very bad at Haskell because they'd just never seen any Haskell. But now they've actually become quite good. Like, they can write full Haskell programs, no problem. And sometimes they don't compile, but it also knows how to read the Cabal error messages, right? So it can kind of fix the problem.
Yeah, I have to say that's very impressive, I think.
Yeah, and I think so. This argument originally, like in 2022, was like, Haskell is great, but LLMs haven't seen enough Haskell code to know about it, so we can't use it. I think that's kind of been shown to it's not relevant anymore with the recent GPTs. And also, because now at the company I work at, we have our kind of own proprietary domain-specific language, and we have 100 or 200 files of that written in that language, and then the LLMs are very perfectly capable of writing programs in our language, right? They've never seen it on the internet. Because it's a very simple kind of relational query language, basically. But the thing is that because all languages are kind of the same, and I think if you know how SQL works, it's not that different from how something else works.
Yeah, and I mean the LLMs nowadays, they seem to have like sufficient reasoning capability that you can sort of tell them the semantics of something. Like you can include that as a I don't know, worst case part of the prompt in case you don't want to like fine tune it. And it looks. I mean, I don't know if you follow Victor Taylin on X, but he's always experimenting with a bunch of his own programming languages and projects, and he seemed to be able to leverage LLMs quite a bit, even though obviously they have never seen it because at least in the beginning it was only on his computer. So I guess this is becoming less of an issue as time goes on.
Yeah, and I think especially with LLMs, it's just that the speed at which things are developing is very fast, And I think if people evaluated LLMs in 2022, they really need to reevaluate them now. Even if they evaluated them, right now what I'm working on is an MCP server. So MCP is this model context protocol, which specifies a way for LLMs to call tools and resources, basically, right? So you can tell it to read a resource, and that resource could maybe be like a location in your program, right? And then you can say, okay, I want to know information about this particular expression or whatever, and then so the MCP kind of gives it a way to understand that, and then they've trained these models to understand MCP, and then these clients use MCP, right? And that came out in November last year, I think, or in March or something, this year.
Yeah.
That's 5 months ago, right? And then, the latest spec came out in July, and it's way bigger than the one that came out. I think there's 2 specs in between or something. But, so even if you evaluated LLMs in January this year, you need to reevaluate them now, right? So I think that's kind of what my message to people is, don't underestimate LLMs because they didn't work when you tried them the first time, right?
Yeah, it's I don't know, they really are quite capable, and all of this, I'm very excited what will happen with this new agentic workflows, because just like you said with Haskell, it feels like it could work very well in an agentic workflow where it sort of tries to maybe fix some part of your code, and it gets a type error back, and then it's you can sort of feed that back into its own context, and okay, well, that didn't work, but now I have more information to try the next solution. Whereas, like you said, with if you have a language with completely unrestricted side effects, it's much harder to trace what went wrong, because it can be I don't know, a million different things.
Yeah, exactly. So I think Haskell is great for LLMs, and but and we're also a community that embraces novelty, I would like to say. We're always excited when the latest language extension comes out. Because I don't think you last very long in Haskell if you don't like kind of weird new things, right? So I think we should embrace these LLMs. They've been very overhyped by salespeople, for sure. but you know, they also are good tools. You know, and we should. I mean, they're probably not going to, you know, eliminate all humans within the next 10 years.
Yeah.
I hope not.
But once we have an LLM that can fix all cabal errors, then we know we have reached AGI.
Yeah, exactly. Yeah, I think that's the limit. If we can solve my cabal issues, then it's AGI for sure.
Yeah. Okay. Yeah. Sorry. I think I have to start wrapping up. But where can people find you if they want to follow the progress on like your work with Haskell and like future LLM things?
Well, mostly on Twitter. I like the mix of kind of academia and you can just joke around. I think I like that. I have a homepage, mpg.is, but that's also linked on my Twitter. And then, you know, you can follow me on GitHub or whatever. I don't think anyone follows anyone on GitHub. But so, you know, don't go to my LinkedIn. My LinkedIn is only, you are not the intent. If you're listening to this podcast, you are not the intended audience for my LinkedIn.
Okay. Yeah, got it.
Yeah. But so mostly on Twitter. And I think people will enjoy my content. I certainly enjoy it myself. You know?
Yeah, you're quite active on Twitter, so it's you're a good follower, I think. Yes, and thank you so much for coming on the podcast, Matthias.
Yeah, thank you for having me.